So with this video, we're going to talk a little bit about the five fundamentals of all chemical reactions and balancing chemical equations. So I'll just throw a mock reaction down here. Let's just say maybe A plus B goes to C plus D, okay? So there are five fundamental things you'll find in all chemical reactions. So one of the first things is that everything on the left side is going to be the reactants. Okay, so we're going to be reacting those two things together, and everything on the right side is considered a product. All right, so we've got our reactant side and our product side. Anytime you see a plus sign, that separates two different chemical species, right? And the arrow, right, that we use in our chemical equations says that, you know, our reactants are going to transform into our products. Okay, so the last fundamental would be if we had some coefficients sitting in the front of some of these numbers. So let's say that 3A plus B yields C plus 2D. So just to kind of review, there's five fundamental things you'll find in all chemical equations. You'll see that there's reactants, there's products, there are plus signs if, you know, there's multiple species, there's arrows that'll always differentiate the reactants from the products, and then there's going to be some coefficients. And if you don't see any coefficients, like if it's left blank in front of the chemical species, that means that it's just understood that the coefficient is 1. Okay? So those are the five things that you'll see in all chemical reactions. All right, so when we are given chemical reactions, it's important that we balance them so that they have the same number of atoms on the reactant side as they do on the product side. And we have to balance and make sure that every atom on the left is accounted for in the right, because remember, there's that whole law that matter cannot be created or destroyed. So we can't create more atoms than what we started off with originally. Okay, so I'm going to work a couple sample problems here because that's the best way to do balancing of reactions, and I'm just going to work a couple of the end of chapter problems. So at the very end, there are exercises for chapter 4, and it's question number 3, and I'm just going to work the very first one, A, which is PCl5 solid plus H2O liquid yields, so see, whenever we write that arrow, we can say that that's yields POCl3, that's POCl, that's a organic reaction species you'll be seeing next year, and HCl aqueous, AQ. Okay, so as you can see, I didn't really talk about them last time, but these letters indicate what phase, you could say, what phase these species are. So you've got solid, liquid, gas would be G, and then AQ is aqueous. That means that whenever you see aqueous, it means that this chemical species is dissolved in water. Okay. All right, so when we are balancing this equation, you have to see what atoms do I even have on the left side and how many of them total do I have. So I've got a P, I've got a Cl, I've got an H, and I've got an O. So I've got phosphorus, chlorine, hydrogen, and oxygen. Checking on the right side, I better have all of those. I've got phosphorus, I've seen my chloride, I've got hydrogen and oxygen. Perfect. So I've got the same elements on the left as I do on the right, which is perfect. Now what we need to do, though, is we just need to count how many there are and make sure that there's equal number on both sides. So on the left side, if I look at my phosphorus, I have one phosphorus only right here. And on the right side, I also currently only have one phosphorus. The number of chlorines I have, on the left side I have 5 total chlorines, but on the right side I have 3, 4. All right, well, there's already a discrepancy, so we're going to have to balance those chlorines out somehow. Let's look at our hydrogens. I've got 2 hydrogens on the left side total, only 1 hydrogen on the right side total. And how many total oxygens? I've got 1 oxygen on the left side and 1 oxygen on the right side. Okay, so that is the, you know, me going around and what I'll refer to as bookkeeping, how many, the number of atoms I have on either side. So the real discrepancy between the reactants, right, and the products is this chlorine and this hydrogen, right? I've got 5 and 2 on the left side, but only have 4 and 1 on the right side. So when I come up here and look at my chemical equation, I'm not allowed to change or add subscripts. So I couldn't just magically go, oh, sweet, I need 1 more chlorine and 1 more hydrogen. Well, I'm just going to say this is H2Cl2, and I'm going to throw some subscripts there. You cannot do that. When you start altering the subscripts, you're actually changing the chemical molecule completely. So you can't change subscripts, but what you can change is you can change the coefficients in front. So right now, remember, this coefficient is, so far it's a 1 because there's nothing there. And so what if I make that a coefficient of 2? So what if I take away that 1 and I say I have 2 HCl? So remember, anytime you put a coefficient in front, you would end up multiplying out that subscript for each of those species. So instead of having 4 total chlorines, if I put a 2 in front of the hydrochloric acid, I have a total of 3 chlorines here and then plus 2 chlorines here, right? Because 2 times this 1, because it's understood superscript is 1 right there, is 2. So now I have 5 total chlorines. Check, so that looks good. And then hydrogen, so how many total hydrogens do I have? Well, again, if that's a coefficient of 2, 2 times 1 is 2, so I now have 2 hydrogens. So actually, boom, there it is. I've just completely balanced the equation. So the coefficients are 1PCl5 plus 1H2O yields 1POCl3 plus 2HCl. So the coefficients are 1, 1, 1, and 2, and that gave me a balanced chemical equation. Let's try one more. Okay, let's do, so that was question 3, part A. Let's look at something maybe a little more challenging, and here we go. We'll try this one. So this is question 3, part D. So I've got solid iron reacts with oxygen from the air, so gas, to yield iron oxide, Fe2O3 solid. So iron oxide is rust. So this is the chemical equation that happens to anything that turns rusty. So you've got solid iron, reacts with molecular oxygen in the air, O2, and it yields iron oxide. All right, so let's look at balancing. So again, starting off, all coefficients are 1. Let me do my bookkeeping here. I've got 1 iron atom on the left, and I've got 2 oxygen atoms on the right. And 2 oxygen atoms on the left for my reactants. If I'm looking at the iron and oxygen on my product side, I've got a total of 2 irons and 3 oxygens. Okay, so this is looking like, so changing number 1 to 2, so both of them are different, right? So I've got a lot of balancing I need to do here. So, and to change the 1 to 2, I could just put a 2 in front of the iron over here, right? So now I have 2 irons and on the reactant side and 2 on the product side, so that worked there. But how can I convert 2 oxygens here into 3? So look, these are subscripted, which means they're going to have to stick together, right? You can't change the subscripts. So when you see that the subscripts aren't going to be working so much in your favor, they're not just ones, then you have to start thinking of like least common denominator. All right, so the least common denominator between the numbers 2 for this O2 and 3 for this O3 in the iron oxide is going to be 6. So in order to make 6 total oxygen on both sides, what would I have to do to these coefficients in front? For the molecular oxygen one on the reactant side, to make it a total of 6 oxygen atoms, I would put a coefficient of 3 in front, right? Because 3 times 2 is 6. So let's put that there. So that would be 6. All right. So for this one on the product side, my iron oxide, to make that a total of 6 oxygen atoms, I would need to put a coefficient of 2 in front. And so remember, 2 times 3 is 6. So now I have 6 oxygen on the left, 6 oxygen on the right. Check, check, check. What have I done though to the iron? So I'm going to put a big check mark by oxygen, but I have to go back and check what happened to the iron, right? Because I put this coefficient 2 in front. So now I have a total no longer of 2 iron atoms on the product side, but now I have 4 total atoms on the product side. And over here, I only have 2 total iron. So I need to change this coefficient to the number 4, right? Because the nice thing about the iron is that it has that subscript of 1. So whatever I put in front of it is how many atoms I'll have. So let's see, so I'll have 4 there. So that looks to me like it would be the proper balanced equation. So 4 iron plus 3 oxygen yield 2 iron oxide. So the coefficients there would be 4, 3, and 2. And remember, that means that I have 4 iron atoms on my left. I've got 4 iron atoms on my right. I've got 6 oxygen atoms on my left and 6 oxygen atoms on the right. So we are completely balanced. Okay, so just to recap, 5 fundamentals of all equations. There are reactants, right? Products, plus signs in between different chemical species, an arrow to separate reactants from products, and then we have our coefficients, right? That let us know what we're going to find out later is the stoichiometric amounts that you need to be able to react to have this chemical equation be true.